Amazon. Thanks for coming, and the hand over to you.
Thank you very much. So my name is Tom Soderstrom. I've been with Amazon Web Services now for 8 months. Before that, I was Chief Technology and Innovation Officer at NASA's Jet Propulsion Laboratory. So obvious, I'm passionate about space. So what I wanted to talk about today is what we're titling the new space economy, and I'm personally very excited about it. So I'm located in Los Angeles. I wish we were all together in person, but maybe one day we will be again. So hopefully you now see the slide that says topics. And I wanted to just cover 4 topics. Why should we care about space? What's this new space economy all about? Who can benefit? And short answer, all of us. What are some examples of this space economy, and what should we do next? And Louis, I'm just checking we're good on the slides and everything. Yep.
Good for me.
Okay, thank you. So in the end, it's not about IT, it's not about data center, it's about answering the big questions. And you can see the big questions here that affect all of humanity. How do we protect Mother Earth? I'm talking about Earth science, being able to, we're in a climate crisis. So how can big data and we all help to solve that? If we one day couldn't divert an asteroid, do we find a place to go? Can we find Earth 2.0? Is or was there life on Mars? And where did the universe come from? Where is it going? And most of all, are we alone? These are the big questions that affect all of humanity. And I believe that with the new technologies and the new space economy, we will answer these questions in my lifetime. So hopefully I live a long time. But this is an exciting time. So let's talk about why space and why now. There is, if you haven't noticed, there's a space bubble right now. And a space bubble is a good thing because it means there's a lot of interest in space. For one thing, if you've ever started a company or done a new startup, you're looking for a larger purpose. Well, what could be larger than humanity and what our future is? There is renewed national interest. Just in the last few weeks, I've talked to 5 different national space agencies that are just coming up and being interested. Why? Because there's a national purpose, big for humanity, but also the cost to participate has gone way down and is going way down. And the skills are going way up. So for a few examples here, if you look at the space budget, so that's interesting for business, it's gone up. It's about 350 billion now. It's going to go up to over $1 trillion in 2040. The cost to launch a spacecraft has gone way down, thanks to the rocket labs, and SpaceX and others. So we can all participate. The cost to build a spacecraft is about 1/15 of it was roughly a decade ago. It's orders of magnitudes cheaper to track a spacecraft. Amazon has created spacecraft as a service where you can just rent time. You don't have to own the antennas. And that's a big deal. I did some cost comparisons at NASA, and this is a good way of augmenting the existing resources. And you can see the rest of it. Much more data, hundreds of times more at much lower data cost because of the cloud and much cheaper storage. It's just the bigness of it creates efficiencies. The increasing in power is doubling about every few years. But when you multiply that with a cloud, you're getting just about unlimited amount of processing and storage. There's going to be a lot of satellites launched. There's SpaceX, there's Kuiper, there's all kinds of other ones. We're going to have about 5,000 satellites in orbit here in just a few years. And that creates new business opportunities. Looking at venture capital, it's doubled in just the last year of interest in space. The Internet of Things, what could that possibly have to do with space? Well, think about Internet of Space things. And Internet of Things is going to become $1 trillion business. So when you multiply these exponential curves, you get a lot of interest. And of course, the new technologies. So I think the biggest thing of all is, and this, I'm so excited to be at this particular seminar because we can stand in the shoulders of giants like all of you in minutes, not years. And that is how we share open source and more. So the interest in space is new. I think there is a new paradigm of how we work. The more complex the IT environment, the simpler we need to make the interface to it. So at NASA and AWS, we still use whiteboards. They may be electronic whiteboards. But the question is, how do we find the answers quickly and how do we tech new questions? There's some key technologies here. So we have learned how to speak. We just speak to the room and you get the answer. You can gesture and it creates an application program interfaces, goes after the data in the cloud and brings it back. So you can just use any way of naturally interacting, and that's Internet of Things. Then all the data can go into the cloud, or we can share it. We can use visualization techniques and analytics to understand it. And then we use machine learning and natural language processing, deep learning, to close the loop and answer the questions. So we have these intelligent digital assistants that can answer any question, just ask the question, or it proactively tells us what we need to know when we need to know it. And this sounds like magic, but it's not. It's here and it's working and it's just getting better and better the more data we have. So AI and machine learning, of course, is becoming consumer items. So now question 2, who can benefit? So in blue here, you have the institutions that can benefit. The government with disaster response, startups, the space agencies can encourage business. The business can use the data for the many different purposes, even farming. So we have satellites from space now that can look at the water table and even tell drones to go and spot water because and look at the spectra that's emitted from the plants that they're in distress. So things become much more efficient. But most of all, I think is that you all, it's the data scientists, the AI experts, and the developers who can benefit from what other people are doing in minutes, not years like we used to do. So I think everybody will benefit from this space bubble. And I wanted to just show a few examples. Here are some of the AWS space customers, and I'm sure we have many others. But I think the interesting thing here is the new use of space data. So we have Capella providing access to satellite data in minutes, all the way to Fireball, I think is interesting here because it can detect wildfires in as little as 3 minutes after ignition. We can then target and send an email to the fire department that can then go and put out the fire. Other examples here, anything from palm oil to protecting the marine environment, to monitoring pipelines and subsurface water leaks. There is no end to what we can do with the space data. It's only limited by our creativity in sharing the data. So how do we protect Mother Earth? Here's a few NASA examples. And it goes back to the big data. We can understand the Earth water model with 2 new satellites going up, SWAT and NISAR, launching in a couple of years. And one is with the Indian Space Agency, one is with the Canadian and French Space Agency. What's interesting here is we realized at NASA that our data centers weren't big enough. These 2 missions alone, their Earth orbiters, will collect 100 times more data than everything we did before. So data centers aren't big enough, but the cloud is big enough. And we learned that you can be new models, cost models, like using a spot market from the various cloud vendors, where you set 90% discount, just use unused capacity, reprocess data. Using GPUs, NISAR learned that they could switch from CPUs to GPUs, and it was 3 to 100 times faster. Once they did that, they realized that you can just keep the CPU code and now switch to whatever is cheaper that day. So I think it's new business models, and it's tremendously exciting to help protect Mother Earth. This is one from California earthquake a few years ago, and here's about automation. So what we can do is we had monitored computers in USGS, automatically spun up computers in AWS, and did, after an earthquake, did an interferograms, pictures from various satellites, overlaid them, and then sent it out to people who had subscribed. one person named Eric Fielding saw this, and he was interested in earthquake faults. And he now detected that fault that's about 2 o'clock going down towards the left-hand side of the screen in minutes without anybody having to sit there and monitoring. So I think that automation is very, very powerful. We can use deep learning and reinforcement learning to do predictive maintenance on satellites. It's going to be important when you have 5,000 of them circling the Earth. And we realized that on the Surface Moisture Active Passive mission. In just about no time, we found 85% of the errors that humans found. And now you could do it every orbit as opposed to once a week. Another example is how we collaborate. So collaborating on virtual islands instead of data centers. So create the piece in the cloud that we cared about and put all the tools we needed for that mission. And it's cut the negotiation time within NASA to, by orders of magnitude. Imagine different countries collaborating. Nobody wants it in their data center for security, cybersecurity reasons. So this provides the ability to collaborate and terminate projects when they're done. NASA is sending an orbiter to Europa, the Jupiter moon. And we experimented with quantum computing, with reinforcement learning, and we found that we could schedule the antennas much, much faster because it really is a traveling salesman problem. So we could now learn about quantum computing and reinforcement learning and apply it to something new. So I think that's the call to action here, is looking for evolving the new technologies. Mars, of course, is our favorite place. And here's Perseverance. It's now on Mars. And what's interesting here is by using cloud computing, and we were able to share the data out across the world. And we were able to speed up the processing by 3 times, which led to less lost drive days on Mars, because it can only drive during the daytime, completely automated. And it's going to have a little friend, the helicopter. So here's the idea of having an experiment always going and using the latest technologies. So helicopter here is actually using something called F Prime, which is an open source flight software. So everybody can participate. And this is coming from Jet Propulsion Laboratory. Finally, we decided to build rovers. And the rover looks like the real Mars rover, but it's built for children, high school and down, to collaborate. And what it makes us do is having hands-on collaboration between different disciplines. And I think that's going to be important. Hardware, software, sensors, programming, and it's built across all the world now. And it makes people more interested in space and engineering and science. So finally, what should we do next? I think we should join the new space economy. The costs are minimal. The benefits are simply astronomical. Experiment and evolve these new technologies and share it. And I think the open source, AWS has something called a data exchange. There are many eScience institutes. I think the key piece is to participate. And I think automation, I mentioned that, is really a key. Collaborating in virtual islands, discovering new creative use cases for space data. I think we're just at the infancy of being able to share all this data. And solving the problems and publish not just the papers, but the data so that other people can stand on the shoulders, on your shoulders and recreate it. And then really it's about helping answering the big questions in our lifetime by looking at space data as an asset and adding to it. So in summary, the new space economy is going from observation to participation. And it's a global movement, and I'm very, very excited to be part of it, and I hope you all participate. So I want to, I will monitor the Slack channels for Q&A, and I very much look forward to any questions and the next speakers. Any questions?
Graham, are you there? Okay, Andreas is not there. So let me take a look at the Google Doc here for questions. I'm sorry, I was not prepared. Yes, there is a question there. Is what kind of advice would you give to someone starting to explore scientific computing, and data lake with the public cloud?
Good. One of the things that AWS has realized is that we need to train people to remove the mundane pieces. So there's actually new classes coming up in how to use the cloud. AWS has committed to train 29 million people by 2025. So being able to not have to own your own computers, go and search. Google searches work really well to find what somebody else has done and add to it. And look at something called SageMaker and other tools for using AI and machine learning. It's much, much easier than it used to be, much easier. And we can reuse data and add back into open source. So I think my big advice is to just try it and get started. It's simpler than you think to get started because we don't have to invent everything all the time anymore.
Okay, I have another question, the last question here. How do we factor in the value of the pristine night sky, which is a natural wonder worth more than anything money can even buy, against these commercial considerations? Protecting Mother Earth, as you mentioned, also includes protecting its night sky, which means fighting against light pollution on Earth itself, but also having better regulation against launching so much space junk.
I think that's a very perceptive question, and I agree completely. I think there will be regulation, and there will be, it isn't just technical, it's policy, it's legal. And I think that is one that will be a concern. Another concern is space junk. How do we deal with it? So everybody needs to be able to safely crash their spacecraft when they're no longer operational. I know NASA, for instance, always leave enough energy to be able to crash a spacecraft, and so it burns up in the atmosphere and doesn't pollute. So excellent question. Pollution is something we have to deal with. I don't have the answer. I just know that it's going to be worked on.
Okay, I think there are other questions, but we're just running out of time. And I think I'm going to pass the bucket to Andreas, who has now joined us.
Yeah,
Thank you very much.
Sorry
Thank you, Tom.
Thanks, Tom. That was a fascinating talk, and I have the pleasure to introduce Richard Dubois to you, and he is actually a senior staff scientist at SLAC, and had been working on, is still working on the Fermi Gamma Ray Space Telescope, and today he will talk about the Rubin Observatory Legacy Survey. And I hand it over to you.
All right, so hopefully you can see that in full enough screen.
That is all good, yeah.
Excellent. Okay, so this is about Rubin and the data facility and facilities. This is actually the first of 3 talks that are related to that. And so I'll be setting up Dominique and George a little bit. And they'll be able to expand on a couple of things in my talk. So the first thing is introduction to Rubin, the sizes, the science mission, and then the data facilities that'll be spanning 9 time zones, and then some of the stuff we need to make this work, and then how do we get going? Okay, so here is a picture from last December of the summit, Sarapaton, Chile. This will be an 8.4 meter mirror. Little side thing. I got to visit a few years ago, and one of the things that was interesting to learn driving up to the summit was that the tunnels are sized to fit 8 meter telescopes. So it's a wide field of view, 9.6 degrees, 3 gigapixel camera, which is being assembled at SLAC now, 6 filters, and the survey operations should start late 23, early 24. Okay, so the science drivers, dark matter, dark energy, solar system, Milky Way, and transients. The transients will come up a lot later, but you can see the various elements of that. Okay, and then just a forward pointer to one of the data sets we're using for testing. So the Dark Energy Science Collaboration put together a detailed simulation of 300 square degrees of what LSST will see in its survey, and we'll be making use of that, and you'll hear more of that from Dominique. But basically, a 300 square degree patch. You can see tracks here, and then zooming in to the fidelity of the simulation. Okay, schedule is important. We are here, and so construction is underway. Commissioning and construction is expected to finish at the end of fiscal 23, and then operations, the survey will start going into here. And there are various data previews that we are going through. The first one is with the dark energy science simulation, and then getting into real test camera data, full camera data, and then the data release. Okay, here's a picture of the team, the data production team that's going to be orchestrating this work. Good to see that Will O'Mullane has just turned up. He's the boss of this operation. And you can see it's distributed broadly across the United States. There's networking interests working their way up to the US, and then the data facilities in France and Edinburgh, which you'll be hearing about. Okay, so here's the kind of picture of the data production system. So we're expecting 20 terabytes a night. We have sequential 30-second images. We'll basically cover the entire sky every few days. The general idea is to make a 10-year movie with some 800 exposures on every spot on the sky. So there's transients that we'll be tracking. So the prompt data products, basically within 1 minute of closing the shutter, we want to be emitting alerts in the nightly alert stream. Over 24 hours, we'll be putting out more prompt products. And then once a year, we'll gather up all the data taken to that point for all years before to reprocess, calibrate, and then make catalogs from that. You can see here, after 10 years, a lot of images, 5 million images. The catalog will be decent size, 15 petabytes, and billions of objects. So these will be set up by data releases, and here are kind of the customers, so community brokers, alert filtering services for the alert streams, and then the data facilities and these data access centers for the data releases. The idea is to have a science platform. You've heard this all through this meeting of bring people to the data, and Rubin is no different. So we expect to have 3 elements of this: notebooks, clearly, web APIs, and a portal. So basically you can export your queries to Topcat or your favorite tools, or work directly in a notebook on top of the underlying system. Okay, so what do we do? Whatever this color is, greeny thing, is at the base. So that's where the data is taken. There's a data backbone that then takes the data up to the data facility, the US facility at SLAC. And then you can see the various activities. So there's the prompt processing, alert distribution. There's bulk distribution to other places. I'll tell you more about QServe, our big database for handling the objects, and then the science platforms to serve the users. And then over here in this orangey color are the other data facilities in France and the UK. So a reminder, large data sets, complex analyses. The prompt processing is pretty prompt. And we expect it to take about a couple of 100 days each year to do these annual processing. So a big deal. Okay, moving the data around. Here's the network picture that we have. So starting in Cerro Pachon, working our way up through South America. We'll end up in Miami. And these are our dedicated links. Then a connection to Atlanta where we hook onto ESNet. And then ESNet will feed everybody up here. So the data facility will come from there, Tucson, then ESNet will talk on its transatlantic links to the Géant and Renator networks for the UK and France. And you can see sort of the sizes. We're looking at least to start 100 gigabit networks to support that. Okay, so now a couple of pictures of just the flows. So down at the base site, and you can read what's being sent along. But basically, shipping the images up to SLAC, it has to get there in 7 seconds. to generate an alert within a minute. We're expecting on the order of 10 million alerts per night. And there'll be a number of community alert brokers watching this feed. So that's how the processing will go. The data release processing, so this is the 200 days every year major campaign. So the same path to get the data, we'll archive it. So there'll be sort of an archive facility. So SLAC is slated to do 25% of the annual processing. France will have a complete copy of all the data and will do half of the processing. And then the UK will do the remaining quarter. So there's a fair amount of traffic over that transatlantic link. When we're talking hundreds of petabytes that are being shipped back and forth. And I have a little sort of cartoon here, which is the picture of the processing pipeline in the current phase for the annual processing. And it's not trivial. So this is the kind of distributed graph that we're going to have to process in multiple sites. So we expect to have hundreds of thousands of concurrent processing jobs and be shipping hundreds of petabytes around. Okay, sizing model. We've been benchmarking on construction error codes now and working with precursor data sets, so HSC, DES. The pipelines are not complete, so our processing estimates are still in flux. We're estimating about 1,200 cores to support the prompt processing. And so during the Chilean night, they'll be kept busy. And I mentioned 25% of the processing at SLAC. So in the current sizing model, we're looking at a couple of thousand cores in the first year, up to 20K for that 200-day turnaround. Currently, we're thinking about AMD ROMs with 128 cores, 512 gigabyte RAM. Sizing model, a lot of data. Here you can just see the sizes. We think this is fairly secure, and given the way the observing is going to go, the data taken will be pretty metronomic in a sense, and so that's pretty predictable. But you can see we're up into 300 petabytes by the end. Okay, so now for the computing systems. So I kind of like this layered picture of computing. So down at the bottom, sort of the base layer is the computing hardware, storage, database services. So it's the physical systems or cloud. Then you have the software components to help manage these clusters. So a lot of familiar tools that have been talked about during this meeting, both continuous integration hub, Jupyter hubs, containers, underlying workflow systems, infrastructure as code, all of that. Then above that, you have your customization. So these are your pipelines and middleware. And so you have the data movement tools, workflow tools. And then on top, you have user interfaces and things like our science platform, the user pipelines, developer services. So this is the stack that we're building. Okay, so a couple of things just on the big catalogs and a tiny bit on the infrastructure, but Dominique will go into this in more detail. So as has been made clear in the meeting, catalogs are key to astronomy. And this just gives you an idea of the sizes. So we're expecting 60 trillion rows in the database by 2035, 10 petabytes of that, 47 billion rows of deep blended objects, yet more about extended attributes about those, 9 trillion single epoch detections, and so on. And so here are some of the queries that we're anticipating people will be executing, and the time spans, the wall clock times that we're expecting these things ought to take, and then crafting a system to do that. So we've custom built QServe, which is pictorially here. We're expecting, as it says here, like 100 queries simultaneously, 10 per second, 50 which are longer for full data set. It's basically a spherical partition of the sky and a distributed database system. For people who are familiar with XRootD, it's actually using the same query mechanism that XD does to find files. So this has been demonstrated to date both on-prem and clusters at NCSA and in the cloud, and CCI and 2B3, and could be hundreds of nodes at peak scale. Okay, now infrastructure is code. So you've heard this already multiple times, so I won't dwell on it. Kubernetes is everywhere now. And basically you want to be able to start deploying your infrastructure as code. And I had this sort of dream that it's the same code across our 3 centers. We'll see how that works out. Okay, so while the agencies were deciding where the data facility would be, Rubin moved ahead with an interim data facility in the cloud, on the Google Cloud. So this was to get going, try stuff out, and cloud hosting seemed like a good option at the time, and still has been. So Google was selected. We have a 3-year deal with them, which should end just before the survey starts. And we are migrating services there to try them out now. And it'll be a real pathfinder for the data facilities. So this interim facility will support those data previews that I mentioned. So the first one, which is happening real soon now, is on the simulated data from DESC. We have a small test camera called the commissioning camera, which will be data preview 1, and then the full 189 CCD camera, LSST cam for the second data preview. And that'll be going up to right before the survey starts. So obviously this is providing integration of the system, getting the team to be operations ready, and then allowing that transition into the USDF. Okay, so just some technology baselines and things that I'm very concerned about is that this is a lot of processing, a lot of data to move. And so we're trying out Atlas's Panda tool for workload management. Clearly, LHC has figured out how to run zillions of jobs concurrently in multi-site. So it'll scale, it'll handle multiple sites, it'll handle heterogeneous sites. So it's being demonstrated now in the IDF. And for data movement, we want the system to just be able to put stuff where it needs to be, when it needs to be there. And we're working on setting up Rusio to make that happen. Again, it's in widespread use in HCP, LHC, and we're counting on that for that solution. We're custom writing the transfer tool from the summit to the USDF because of this latency. Not entirely clear a tool like that can figure out what to do in time. Okay, I'm getting near the end. So all of this is going into a shared data facility at SLAC. It'll be shared across projects at the laboratory. And you can see a list of many of those projects. And you can see CPU, disk, and tape. And currently the system has about 14,000 cores, about 7 petabytes of storage. It's ramping up from the existing clusters of similar size, which are being aged out. And what we're seeing is basically the light source, X-ray light source, will be dominating CPU. You can see their bit of CPU here. And then Rubin's is up here. And then storage by a long shot is being dominated by Rubin. And you can see that here. So we're undergoing some physical transitions from the existing computing center now in our lovingly known Building 50 into our Stanford Research Computing Facility, and then its expansion there. So that's under active planning to be ready in time for the start of survey. Okay, so we're getting going. The SLAC was selected as a data facility early this year. And so we're wrapping up for a year from now to be starting to show initial data facility functionality, be able to take over from NCSA in fiscal 23 for operations starting in fiscal 24. So our plan is to make big purchases right before operation starts so that that the stuff isn't getting old fast. And what we're doing now is putting in modest hardware to demonstrate the system and to build up the team and all the working relationships. Okay, so just a quick recap. So this is a sizable activity. Over the 3 data facilities, it'll be tens of thousands of cores, exabyte of data pretty much. We're going to bring 5,000 plus users to the data. These annual reprocessings are going to take a good fraction of a year across 3 sites. We plan to make use of other people's tools, so in particular the LHC tools for workload data movement. And we're building on the experience from NCSA and the Google IDF. And that's it.
Thank you, Richard. Great talk. I'm just checking the document. I have one question from Knut Olsen there. Is QServe being used for applications other than Rubin? And as a follow-up question, is it periodically evaluated against other DB technologies?
Sure. So I might defer to Will a little bit on the other applications using it. I know that Will has been regularly studying other database technologies and has not found one better yet. The thing I'll say is that I know that SLAC and the LightSource people are very interested in QServe as a potential technology there. So they're keeping their eyes open for that. Will, do you want to say anything?
Yeah, I mean, it isn't in use by anybody else that I know of, but also it hasn't really been production quality enough for people to use, I think, until this year. We've seen some pretty good demonstrations with 50% of DR1, so billion row catalogs with good response times along the lines of what we were showing. So I think it's become a possibility if people are interested to actually try this out for different catalogs.
Okay, I think that's answering that question. I don't see, well, there are a few original ones here. So we have one which says, how and when will the data be transferred to all the IDACS?
Sorry, I shouldn't have said that. So the IDAC system has been set up this year. And so I think we're still trying to understand how they're going to work as a network and how the data facilities will feed them. So they'll be fed from the annual data releases. And so essentially after the 200 days of processing, putting up the catalogs, most of the IDACs are hosting a light version of the catalog. And so we'll have to define what that means, potentially custom to the various places, and then the mechanisms for getting it to them.
Mm-hmm. Thank you. We are now about 5 minutes after time. I think I will defer the rest of the questions. There are 2 others in here. And thank you again. And then introduce the next speaker. And the next speaker is George Beckett from the University of Edinburgh. And he will also talk about, and he says LSST, which I think is fine because lots of people still know that name, and the UK plans for an independent data center. George, over to you.
Thank you, Andreas. Can you see my slides okay?
Yeah, looks all good.
Excellent. So you're totally correct. We are still to do a proper rebranding exercise. In the UK, we are still named after the survey. I've not yet moved to the Vera C. Rubin Observatory naming, but I'm sure that will come soon enough. But I'm going to talk a little bit about the plans happening in the UK around our involvement in LSST and the Vera Rubin Observatory. It's sort of in flux at the moment, as I think some of you will know. There is an in-kind contribution process that is midway, maybe a little bit past midway through. And so some of the things I say here are assuming that those in-kind negotiations go as we hope. My slide won't move. Okay, it's just a bit slow. So I'll start by giving you a very quick overview of how the UK is organised. So I think one of the positive things about the UK is that all of the astronomy groups have agreed to work together. There are 36 significant astronomy groups, and there should be 37 logos there. That's because one university insists on having 2 groups, but there are 36 universities that all work together and have formed a consortium called the LSST UK Consortium, and have agreed to work together to sort of maximize the potential benefits that they can extract from the Rubin Observatory. The consortium has gained some responsibility and authority from the funding agencies in the UK. So we are now responsible for securing and managing funding for the whole UK programme, and have created something called the Science Centre programme that I'll talk a little bit about in a couple of slides. And we're also a delegated authority for administering Rubin data rights. Under the old mechanism, each international partner would pay a subscription to secure data rights for a number of astronomers. We in the UK have an allocation under the old system, which will change very soon, but we administer that through the consortium, giving data rights to UK-based astronomers. Some of the key names that you may be familiar with in the UK consortium. Our project leader is Bob Mann, who's based in Edinburgh. He's my boss. Our project scientist is Stephen Smart at Queen's University in Belfast. We have a commissioning coordinator, which is a sort of UK commissioning coordinator called Graham Smith from Birmingham. I share my project management role with Terry Sloan. Both of us are in Edinburgh. And the consortium's current board chair is Mike Watson from Leicester. Our governance is probably fairly standard. The sort of authority is the consortium board, which has representation from all of our institutions, and they delegate day-to-day running of the program to an executive group with the obvious membership. And alongside that, to the left, we have a science working group, which is chaired by Stephen and includes representation for all of the sort of key science areas. So links to the Rubin's international science collaborations, but also representation for all of the UK-based astronomers. And on the other more pragmatic side, we have a project delivery group, which is responsible for overseeing all of the actual work that's being done in the UK, which is split into 2, soon to be potentially 3 streams, and I'll talk about those in turn. So if we look at the Science Centre programme, it has 2 sort of top level objectives. The first is to secure for UK astronomers the access that they need to properly do astronomy with the Vera C. Rubin Observatory datasets with the LSST survey, but also to enhance the potential scientific return of that observatory's data by exploiting, for example, links with other surveys and other facilities that the UK is involved with, and also developing downstream processing and products from the LSST survey data. And the second objective is to secure intellectual leadership for the UK community's priority science areas, so that we can influence as best we can the operation of the Rubin Observatory, and hopefully, as I'll explain in the near future, run a data access centre that serves the full Rubin Observatory datasets to the community. The programme has a roadmap that spans a little over 20 years. It's actually going to extend slightly, as I think many of you know, there's been some delays around the global pandemic, which means we will push out our programme a little bit further than 2033. But the programme has been pretty stable now for a while. It has 4 phases. We're currently roughly midway through a second phase, which is named the commissioning phase. In early 2023, we are moving into an early operations phase just before operations begin. And then later on, we'll move into a standard operations phase. And we have a forecast budget for this work of around about £56 million. And that includes capital infrastructure budgets for a data access centre and for our contribution to data release processing that Richard mentioned earlier. But the infrastructure comes through a separate line called IRIS, which I'll tell you a little bit about. So I mentioned the 3 threads of activity in the program. The first thread is called the DAC, And as you might guess, that is to design, deploy, and operate an independent data access center here in the UK that will serve at least UK-based astronomers. And our hope is through the in-kind proposal scheme to actually serve international Rubin community. The dev thread is looking at developing of software and services that augment what is provided by the Rubin Observatory, often referred to as user-generated products. So these are derived data, derived services from the core functionality and data provided by the Rubin Observatory that support specific science areas and specific science goals. And we also have an ambition to be a community broker, receiving the nightly alert stream from the observatory. And finally, there is a data release processing thread, which is yet to kick off, but very soon is likely to kick off, and that is focused on making sure we deliver our contribution to the data release processing. As I said, our infrastructure won't be dedicated LSST UK infrastructure. It will be provided by a consortium called IRIS. This is different to the IRIS that many in the US will be aware of. It's a UK-based e-infrastructure consortium, and it is looking to ensure that we get funding and deliver sufficient e-infrastructure to support all of the major UK experiments and facilities that are going to operate over the next few years. So these include national facilities around neutron sources, laser facilities and the like, but also major experiments in particle physics, astronomy, nuclear physics, and so on. So for example, LSST UK is a key element of that, but also SKA and Euclid, which are telescopes that the UK has a significant involvement in. It's very much an infrastructure as a service. It provides computing through, at the moment, 3 flavors. You can get HPC computing, you can get high throughput, which is effectively grid or UK's element of WLCG computing, and there is an emerging area of cloud computing. It also provides various storage, file systems, object stores, tapes, access to networking, the UK academic network Janet, and beyond that through Géant, and as Richard pointed out, across ESNet into the US for the significant data transfer requirements of the Rubin Observatory. And it provides some low-level administrative services, resource allocation, authentication, authorization type services, and security, a joined-up security approach. So LSST UK is a partner in IRIS, which means not only do we receive infrastructure from IRIS, but we also, sorry, I'm just checking my time. We also contribute to the strategy, help to shape the procurement and the development and delivery of infrastructure. And we in fact operate one of the IRIS sites in Edinburgh, a relatively modest cloud site, which will form a significant part of our DAC. So let me look at the DAC activities. I'm always nervous when I present this diagram because I'm colorblind, and I'm conscious I've put various colors on here which may or may not be the colors I tell you are. But I think the only thing you really need to take away from this diagram is that we've sort of divided our DAC into 4 or 5 elements. Primarily, we aim to reuse as much technology, software, and services from the Rubin Observatory as we can, and to invest our effort into those extra or downstream services and software that will allow us to generate user-generate products, that will allow us to integrate with other surveys that are key or interesting in the UK. In orange, excuse me, in orange, I've highlighted services that we're developing for our community broker, or our candidate community broker, which is called LARSA. And I've also, in purple, I think, highlighted how we hope to integrate or at least access third-party surveys, third-party astronomy archives that will be used in conjunction with Rubin Observatory data to promote different science. And a key element, of course, is that we need to be able to expand the DAC into larger scale computing resources on IRIS or elsewhere for significant campaigns, the things that go beyond individual or small astronomy groups, the kind of things that would be organized by international science collaborations, for example. During phase B, during this commissioning phase, we have a roadmap for our UK DAC, which effectively means delivering an iteratively more mature version of a prototype DAC on a roughly annual basis. We're currently in the UK DAC 1 phase, which is the second iteration of our DAC. And you can see, I'm not going to go through the details on this slide, but I will share the slide so people can look afterwards. We have a platform which throughout will be some form of Iris platform, mostly cloud-based. And we're delivering an increasingly mature set of functionalities based primarily on the science platform, but also incorporating other elements, UK-specific science and services, but also those back-end services like QServe that Richard talked about in his talk earlier. In terms of data, there isn't any Rubin Observatory data at the moment, but we are serving a number of ancillary data sets that are of interest in the UK. And you can see there UKIDS, the Zwicky Transient Facility Survey data. And we have ambitions to host and serve Rubin Observatory data previews once they become available, if that's supported. Other rows deal with the access mechanisms. Early on, we were relying on UK-based access mechanisms or European access mechanisms called EGI check-in. We're moving into what's called IAM, which should be compatible with the Rubin Observatory authentication authorization strategy. And then you can see documentation. Again, we're trying to reuse as much as possible from the Rubin project and only create documentation that we need for added value elements. And our service desk help desk is currently fairly modest. It's an email and a GitHub issue tracker, but it will expand over time once we understand better what the observatory plans are. In terms of tactics, as I've said, I think probably the headline tactic for just now is that we want to reuse as much from the observatory as we can. The observatory team is much larger than ours and has significant experience that is best captured by working with their software and services. We are prioritizing extending software and services into areas that are not potentially covered by the observatory, user-generated products, and integration with ancillary surveys. We also have to address some infrastructure differences. It's highly likely that the UK data facility will run on a different infrastructure to either the US or the French data facilities. We are primarily based around OpenStack, and okay, this isn't a particularly good list, I agree, but it's showing you that the underlying services on which we rely on, we have to fit into the interfaces and the services that are common across all of the IDACs and across the data facilities too. And we're also looking to collaborate with other UK IRIS experiments, as well as gaining advantage from sharing infrastructure with other major experiments. There's an opportunity to share expertise. And for example, the telescopes such as SKA and Euclid will be facing similar challenges to us, but also beyond astronomy, things like RUSIO that Richard mentioned, distributed data management, is something that's at the heart of forthcoming LHC developments and is likely to feature in many other of these experiments too. Sustainability is a key. In the UK, we're still very much based on project funding, which means very much finite life funding, but we realize that the services and software developing have to run for 10, 15 plus years, and capturing the knowledge and the understanding of the software that means we can sustain it throughout the operational phase of the observatory is very important. And we're working with a UK-based institution called the Software Sustainability Institute to do that. In terms of current DAC activities, I'll quickly touch on these, but in very little detail, so please follow it with me afterwards if you wish. We are running a version of the science platform. But also, we're also, I think, contributing to the science platform. So we've deployed it on OpenStack, and we've fed back to the US team, the Square team, on fixes that we've identified and implemented to deal with some of the compatibility issues between different platforms, and also elements such as authentication and authorization. We are running an instance of QServe. That's actually a lie. Our instance of QServe is currently broken, but we should be running an instance of QServe, and that's hosting a survey dataset dataset called UKIDS, which maybe not an obvious match to LSST for many, but it's a fairly substantial and a well-used UK dataset, so it's a good first test for QServe in the UK. We're also doing some modest pipeline processing work. We were involved in the Dark Energy Science Collaboration's Data Challenge 2, that should say, sorry, DC2. And we're also doing some data fusion experiments using HSC data as a precursor for LSST with infrared data from Vista. And we're setting up various ancillary data sets just now, which will be used throughout the life of the survey to support added value and extra astronomy. If I look at the dev activities, these are the added values, and I've put a disclaimer on this slide because I am not an astronomer and I am presenting other people's slides, but I will do my best to do that. We've got 4 or 5 here that I wanted to quickly highlight. Coming back actually to that Vista survey and our interest in the UK in looking at the astronomy that's possible with multiple surveys. Vista is a good candidate for combining with the LSST survey. It's a complementary bands, it's looking at the infrared spectrum, and it has excellent overlap with the coverage of the Rubin Observatory survey. But to use it effectively, you really need to process both the Vista and the LSST survey data together, and also to do catalog level photometry together as well. So we're running a joint pipeline using Vista and HSC as a precursor for LSST. Low surface brightness science is another aspect of astronomy that's very important in the UK, and potentially the LSST survey has a great potential for supporting low surface brightness science, but that does hinge on how the survey data is reduced, and specifically how things like the subtraction of the night sky are dealt with, because low surface brightness science is dealing with objects that are potentially fainter than the night sky, and so very easily affected by the way that you do that. The team in the UK, mostly in Liverpool, John Moore and Hertfordshire universities, is working with a team in Princeton on the algorithms, and they've done some experiments where they inject model galaxies into the models and then measure the effects of the sky subtraction. As you can see on the image here, this is a particularly bad case, I suspect, but dealing with faint objects with the current pipeline configuration and calibration produces some challenges for low surface brightness science. And the team is hoping to work with the DM team representing the Galaxy Science Collaboration to improve or tweak that pipeline to better address sky subtraction in the algorithm. Catalog cross-match at LSST depths is potentially challenging because it's very difficult to match up sources from different catalogs. There's a group in the UK that's looking to employ state-of-the-art algorithms better designed for dealing with crowded fields, and to use those to provide better cross-match. And we plan to host a number of cross-match catalogs in the UK that will allow you to find correspondence between Rubin Observatory objects in the LSST survey and objects in a number of other surveys to support multi-survey science. LASA, which is our candidate community broker, LASA is Irish Gaelic for flame, which I guess has some analogues with an alert stream perhaps. So the candidate is aiming to provide access to the alert stream from the telescope in a way that's familiar to survey astronomy. So they have created technologies, interfaces that provide you with SQL-like ways of defining the queries that you're interested in. You can develop things such as watch lists, which I think were discussed yesterday for Antares, and you can also take your own stream from the LASA service, effectively filtering down the full alert stream to something that's manageable for a smaller group or a local user group. One of the big elements of LASA is a system called Sherlock, which is an AI-based context classifier. And what it does is it takes alerts from the alert stream and it matches them against roughly 40 published catalogs and uses that information to effectively classify what kind of object it is you're seeing. technologies that underpin it are pretty familiar to people at this meeting. We've heard a lot about them over the past few days. The stream is based on Kafka, and we are using scalable database technology Cassandra, which I know actually was mentioned a couple of days ago. People had found hadn't been particularly scalable to the requirements they needed. So far for us, it's been pretty effective. We're providing a range of interfaces to users. I'll go to the next slide actually, which talks about our current version of LASA, which supports the Zwicky transient facility. So we currently ingest the nightly alerts from ZTF and expose them to users who can then filter, annotate, and follow up on those. There's a web interface which provides most of the functionality users will want. The URL is at the bottom of the slide, and I believe it's a public service which anybody can access. You may need to create an account, but you can get to it there. So you can query, you can create watch lists, you can create filters on the alert stream, and then you can have events delivered to your inbox or delivered on as further Kafka streams to be consumed by your own service. We also have a notebook service, Jupyter Notebooks, which provides you with a bit more flexibility, and an API, which allows you to write your own services and software against the LASA services. And in fact, the Zooniverse project is currently working with us to exploit those APIs to take a feed from LASA for their own science use cases. Spectroscopic follow-up is something that's been talked about several times. The UK is involved in a spectroscopic telescope called Foremost, and a team from the TIDES survey who are looking to identify as many type 1a supernovae as possible are currently working with the Rubin Observatory to model the potential for spectroscopic follow-up of supernovae candidates that are identified in the survey. And based on the survey strategy and the cadence that's used, you can significantly impact the number of candidate supernovae that you can follow up. So here in the UK, we're currently modeling the potential benefits or the potential impact of different survey strategies on the potential to identify supernovae. And then we're also working again with the LASA team to create an automated identification and follow-up mechanism that can be plugged into Foremost to allow you to do spectroscopic follow-up in the days following detection of potential supernovae. They're the main dev activities that are of interest to the UK DAC and the ones that are most likely integrated with the UK DAC, but that's not the full story. We are involved in a number of other dev activities, and I just wanted to quickly mention them here so as I didn't miss them out. The team in Oxford has been a key part of the development of the survey camera, working on sensor characterization work and working with one of the CCD manufacturers who's based here in the UK. And also we work with the Dark Energy Science Collaboration, and we've been involved in running survey simulations with them and developing software ready for data analysis at production scale. So I think that's pretty well all I have to say. What I've tried to explain is that in the UK, I think the fact that the different astronomy groups have been able to work together and form into this collaboration consortium has really given them the opportunity to sort of maximize their exploitation of the Rubin Observatory, and so far it's been working very well. The UK has ambitious plans to build on what the Rubin Observatory is doing. We'd like to run our own UK DAC, potentially an international IDAC, serving the Rubin community wider than the UK. And we also have ambitions to run a community broker here in the UK too. A lot of our effort is focused on exploiting the LSST survey and generating user-generated products and integrating ancillary surveys in to maximize the astronomy that's possible. And we are hoping to be a part of the data release processing for the observatory itself. We don't just want to take though, and hopefully, although we're relatively modest compared to the US team, we do want to be able to contribute back into the international community to make sure that LSST or the Rubin Observatory is as successful as possible for everyone. Thanks very much. I think that was my last slide. Cool.
Thanks, George. Great talk. Let me see what kind of questions we have. Switching back here. I don't see any of the on the Google one, except my own, which is actually about the network. So who is paying for the network?
So the network is expected to run on the existing academic infrastructure. So in the UK, the academic network is run by an organization called Janet. And over the past few years, it has been going through a significant upgrade. We now have pretty well 100 gigabits per second across all of the major infrastructure. In fact, in Edinburgh, we're running local up to 400 gigabits per second. And so our expectation is that that will actually keep up with the data transfer rates that are required for LSST. Compared to some of the other experiments we're involved with, such as SKA and maybe even things such as Dune, we believe actually our network requirements are relatively modest.
And that holds for the intercontinental network as well?
Yes, let's say yes.
That's why I'm asking.
Yeah,
Okay,
well,
I
mean, we are in early conversations with ESNet and so are the US data facility, and our expectations are so far that this is actually well within the capacity of the existing international connections between ESNet and Géant in Europe.
Okay, thank you, George.
Thank you.
Since there's no other question, I take it to the next talk, which is by Dominique Boutigny, and obviously also about Rubin and the DESC computing organization in France. Over to you, Dominique.
Hi. Yes, so I am Dominique Boutigny. I am from CNRS IN2B3 at LAP in Annecy, and I am going to speak about the Rubin computing and a little bit about DESC, Dark Energy Science Collaboration Organization at IN2B3. So first, let me introduce the IN2B3 Computing Center, which is absolutely central in this project. So this IN2B3 is this nice building here. It's located in Villeurbanne, which is close to Lyon in France, not far from Annecy and not far from CERN, from Geneva. So it serves the high energy physics and nuclear physics, astroparticle and cosmology communities since several years. There are supporting 80 projects and experiments. There are 2 computer rooms covering over 1,700 square meters, and there are approximately 70 computing engineers who are in charge of running the computing center. So the computing center is specialized in high throughput computing, HTC, and data processing. They also offer some small scale HPC, but really small scale. It's not an HPC center. It's really data processing, GPUs, notebook service, which is becoming more and more used in the community, virtualization services using OpenStack. Databases, many kinds of databases are supported and offered by the computing center. And they also have an excellent network interconnections with the national RENATER, at the national level, through the RENATER, which is the French NREN, at the European level through Géant, and at the worldwide level. If you are interested in a virtual visit, there is a very nice one which is available at this address. A few pictures of the computing center. That's the most recent computer room, which, as you can see, is very modern design. No waste floor, everything coming through the roof, water cooled, good power usage efficiency, and so on. So this is the part which is running batch jobs, and the capacity now is 60,000 batch processing slots in parallel. And the main batch system used is Grid Engine, and they are also supporting HT Condor, but at the moment which is mostly limited to the electric computing grid. But it may change in the future, especially with LSST. This is the tape, one of the tape library. There are 80 petabytes in use for a total capacity of 400 petabytes. All this tape storage is accessible through tape robot, as you can see here, and through the high performance storage system HPSS. For the disk storage, there are at the moment 40 petabytes of disk storage. They used to support GPFS and now moving to SFFS. And there is also a large amount of storage using Dcache, which is an heritage from LCG, from the LHC computing grid. So LSST, Rubin LSST and IN2P3, there was a memorandum of agreement which has been signed in 2015. Here is the first page of this agreement. And through this agreement, we decided to create what is called in the document a satellite data release processing center at CCI2P3. Where IN2P3 will be responsible of 50% of this data release processing. CCI2P3 will hold a full copy of the input and output datasets. And IN2P3 will provide the computing equipment and labor. And the data release processing management is under the project's responsibility. So it means that we are not responsible to make a parallel data release processing systems. We are part of a global system which is under the project Rubin responsibility. And in exchange, France gets some extra data access rights. But this is old. This is from 2015. Since then, there was some reorganization inside LSST Rubin. So this agreement will have to be revisited. But we do not expect that the big picture will change a lot. And as a remark, it's also crucial to coordinate with SLAC, who is hosting the US data facility, as well with the UK data facility, if it is confirmed that 25% of the computing will occur in the UK. So what will we do at the French data facility? So our commitment to Rubin LSST is to import an integral copy of raw data. So it means the raw data here means images, calibration, and everything necessary to process the images from the USDF and store it in a permanent storage. So in this way, we'll have a secure copy of the raw data. This will be done on tapes and stored in the robots. Annually, in fact, annually means twice the first year, we will locally process 50% of the raw data collected since the beginning of the survey. So it means that every year we are going to reprocess everything from scratch. We'll produce calibrated and co-added images. Co-added images means that the images are being stacked one over the others in order to make a deeper image. And we will prepare data to populate the catalogs. We will export the locally produced data products to the USDF and import USDFs and UK DFs in order to have to constitute a full copy of the data. We will store an integral copy of the data products on permanent storage. So that's our commitment to Rubin. Our commitment to the French Rubin LSST community, I mean, I insist that I'm speaking about the French one. We will keep a copy of the relevant data product on disk for usage by scientists. And this will be at least the 2 latest data releases. And we will provide the tools necessary to maximize the scientific return on our investment. So we will build some international data access center plus computing environment. But the international part of the data access center is still to be defined and to be negotiated with the funding agency. So here is a forcing picture. This is a slide from Fabio Hernandez. be careful of the numbers here. This is under revision. So this was derived from the previous Rubin sizing sizing model, and this is going to change, but the large picture is right. So this is a batch farm. We'll start with 22,000 core to 123,000 cores. Login nodes, of course, data transfer nodes. Ultimately, we will have 100 gigabit per second link between CCI into P3 and the USDF. At the moment, we have 20 gigabit per second links between dedicated for Rubin, and this will be upgraded before LSST startup. The disk storage will start at around 3 petabytes that we already have up to 60 petabytes, and the bandwidth will increase in order to support this change in the data volume. Sorry, that was for the catalog database, and the same thing for the disk storage from 10 to 55 petabytes, and for the mass storage on tape from 9 petabytes today to 121 petabytes. Of course, these dates here will change a little bit. We know since last week that officially LSST, the LSST survey from Rubin will start with 1 year delay, so starting in October 2023, and moving things by typically 1 year. By experience from LXC, for instance, the complexity is not in the individual components of a computing system, as sophisticated as they are. I mean that you can have some very sophisticated components, individual components, but in principle, ultimately, you are able to make them work. The difficulties arise from the interaction between the components. And this was absolutely obvious in the LXC computing, especially at the early time. So we need to get prepared long before the data starts to flow in order to tune the infrastructure, in order to identify the bottlenecks, correct the faulty components, and think about and set up the most adequate monitoring tools. Monitoring tools are crucial in order to understand all these possible issues. So data previews introduced by Richard in the first talk are of crucial importance in order to get prepared. So DP0 is data preview 0. We'll use the simulated data from the Dark Energy Science Collaboration simulated survey, DC2. DP1 will use the commissioning camera, and DP2 will use the commissioning data with the full Rubin camera. So Dark Energy Science Collaboration which will provide the data set for DP0, simulated 300 red square degrees, corresponding to the Rubin wide field, and with 5-year depth of LSST. It also simulated 1 square degree corresponding to the deep drilling field. So if a field where we are coming several times every night in order to be much more deep. And the simulation is also supporting the transient sky by adding supernovas, for instance, or things like that. So this dataset provides an excellent test case for both data release processing and also to test the data access methods. So this DC2, this image has been shown by Richard, is the following. So this is all the tiles in the skies which has been simulated. So here is a zoom on this tile here, and here is a zoom on a specific galaxy cluster. So this is simulated images, and you can understand from this image the level of precision that this simulation is providing. The paper corresponding to the simulation is available here. So the DRP processing for this simulation occurred at CCI into P3. And it was very complicated, much more complicated than expected at the beginning. So the input is 5 years of LSST corresponding to 75 terabytes of raw images. The processing is multiplying this by a factor of 10, approximately a little bit more than that. And this is both CPU and IO intensive. We use more than 120 million CPU hours in order to process this data. And we had a lot of issues. So for instance, processing the deep drilling field, we encountered some problems in performances. And for some of these small fields here, we had some cases where it needed more than 800 hours to complete and also requires large memories. So we had some scaling issues, clearly. And we have to understand that DC2 is small. This is here you have the DC2 footprint compared to the Rubin footprint. 300 square degrees is only 1/60 of the full survey area. And the whole DC2 is only 8% of 1 Rubin year. So this shows us the size of the problem and the importance of the data preview 0 in order to be more prepared for the real data set. One of the big things that we have to do in order to process the data is to handle the workflows. And in Rubin software, we have a very important component, which is called the butler, which is central in the software. And basically, what it does is to establish the relation between high-level metadata and the actual file storage location, the actual file location and storage. So for instance, you can have a filter number, the filter name, a tiles number, visits. You give that to the butler, and the butler is able to retrieve where is the dataset, the image, or the corresponding catalogs. This has been completely redesigned recently to separate the I/O operation from the processing task, which was absolutely necessary to take full advantage of modern workflow engines. And the new butler is also supporting several types of storage. So we can have some standard POSIX storage. It supports Amazon S3 like storage. And also recently we developed at CCI Into3 a WebDAV interface, which will allow us to use the LCG, to reuse the LCG decache technology, and potentially will save a large amount of the storage cost. The butler is also using a PostgreSQL database in order to keep this relationship between the metadata and the various datasets. And this is typically the kind of things that we will have to monitor in order to avoid bottlenecks, because the database access here need to be extremely performant if we want to be able to scale. A second functionality of the butler is to analyze a task in order to generate a graph which describes the whole processing in terms of quantum units with all their dependencies. In fact, this is a DAG. Here you have an example here where you have an individual task and all the relation between all these tasks. The Rubin quantum graph needs to be converted to DAG interpretable by workflow engines that will distribute the computing load to the computing center batch system. In other words, you cannot do anything with the Rubin quantum graph by themselves. You have to convert them to something suitable for being processed by a high-level workflow. There are existing interfaces to HT-Condor, to Parcel, which has been developed by DESC, not Parcel, but the interface, to Pegasus. And we will experiment with Panda, which is the workflow system used by Atlas in the LHC, and also consider Dirac, which has been developed for LHCb. So the final system will have to be managed centrally and able to distribute tasks on the 3 ERP sites. This centrally managed system will not be ready for data preview 0, but we have to work towards these objectives. In the meantime, at CCI2P3, we intend to redo the data preview 0 processing in parallel in order to get trained. QServe database, this has been also presented by Richard, introduced by Richard. This is a distributed chain nothing architecture, SQLite, so it means that you can make SQL queries. There is a geometry which is built inside QServe. Here you have an example, so it means that all the data are distributed on the servers according to their location in the sky, following these small tiles here. And it also has a shared scan concept in order to reuse partial results in order to speed up query time. So for instance, if I am doing a query, QServe is able to make is able to store the result of the result of the query in order to be reused by another one. So QServe is an in-house development by the Rubin project. It's a huge effort. I don't know exactly the number of man-years, but it's really huge. But despite of that, we need to check how it matches the scientific needs from the science collaborations. Basically, the QServe has been handled as a technological project and with scientific inputs, of course. But we need to make sure all the time that the scientific needs are met. And these scientific needs are provided by the science collaboration. Don't forget that with the Rubin organization, the science collaborations are separate from the Rubin project. We can also ask the question in a different way and ask ourselves how science collaboration can make the best possible use of a database like QServe. So we are operating at CCI2P3 a QServe test platform since several years. And in fact, we are already now at the version 2 of this platform. You have a picture of the first version of the platform with the chief developer of QServe. At the moment, this is 20 workers with 256 gigabytes of RAM, 64 terabytes of disk. We have 15 workers for QServe, 2 workers for the Rubin Science platform, and 2 masters. This is a Kubernetes on-premise cluster. And we benefited a lot from the expertise from the local QServe developer, which is based in Clermont-Ferrand. For data preview 0, Rubin is operating another QServe cluster, which is deployed on the Google Cloud using GKE. And the DESC DC2 catalogs are loaded on both clusters. So we will compare the QServe performances and maintainability on the Google and on our on-premise installation. On the Rubin Science platform, QServe will be accessed through the TAP protocol. So it will be also interesting to check and to compare direct SQL access that we will be able to perform at IN2P3 to VO-TAP access. That will be the only way to access QServe on the Rubin Science platform. So we did some early tests with QServe. We had we converted in order to do this test, we converted the DESC queries using the internal DESC system into SQL queries and check performance and usability. So to give you just a flavor of what we obtained, a full scan is performed on 2.2 billion lines is performed in of the order of 1 minute. We had also some use case example using Galaxy clusters, and we were able to implement these queries on QServe using the capacity of doing parallel queries on the system, and we got reasonably good results. But we have to be very careful because there are large cache effects, and this needs to be repeated on larger databases. We also need to collect a set of other realistic use cases and check how they can be solved. It's not clear to me if QServe is well adapted to large-scale analysis requiring to seek through the entire dataset. For instance, how are we going to implement whole-scale correlation function computing on using QServe? I am not sure that this is the best tool in order to implement that. And maybe we'll have to implement some parallel packet file data access using DESC or Spark, and that may be more efficient. But this has to be proven, and we need to have a real use case in order to do that. The last part of my talk, I will speak about the Rubin Science platform, which has been already introduced also by Richard. So the Rubin Science platform will have portal functionalities, notebook functionalities, and will also provide some web APIs in order to access to the data. It heavily relies on Kubernetes technology. This is a typical example of infrastructure as code design, using all this kind of technology here. We are deploying the Rubin Science platform at IN2P3 on two sites, at CCIN2P3 and at Lab. We will have some beta testers at CCIN2P3 in order to access the data preview 0 data. And we also foresee to assess the Rubin Science platform in the framework of the European project ESCAPE in order to compare to the official S3 science analysis platform, for instance, and check if this ASAP could reuse some components of concept. The flexibility offered by this kind of technology comes with together with a tremendous complexity. The Rubin Science platform for data preview 0 is deployed on Google, as I said previously. The IN2P3 ones will be is on bare metal, where Kubernetes is much more complicated to manage. Here is an example. This is the Argo CD dashboard, where you have a dashboard with all your services which are running on the Kubernetes, and you are able to immediately spot if something is running well, which is green, or if something needs to be resynced, for instance. So here are my personal views on Kubernetes. So following a personal time investment of, I estimated it to be of the order of 200 hours, with the help of two experts. I think that Kubernetes is clearly very nice, fascinating computing tools. I insist on the fact that it is fascinating, but designed to run in a commercial cloud environment. And it's clear for me that Kubernetes will not disappear tomorrow. And it will probably be even more complex in the future and even more difficult to run on bare metal clusters. And the portability of a complex Kubernetes-based application is still unclear to me. The main question, in my opinion, is to understand how our science data centers can survive with this technology. The answer is not obvious, but we have to think about it. And we have to think about it as a community and experiment about it in order to understand where are the real issues and how we can solve them. And if I had a recommendation for people who want to start on Kubernetes, I think it's really vital to hire or to train a true Kubernetes experts in our data centers. And of course, if we can afford to pay them, because I think that these kind of people will be extremely demanded, will be extremely, will be looked for. So even if we can't reliably deploy the full Rubin Science platform at IN2P3, it's still not completely clear if it will succeed. We still have the most critical parts. And inside all this system, we have the QServe database. So this is working, and this is working well, and we are able to manage it. And we have also have a standard container-based Jupyter Hub notebook platform. So at least we will be able to provide the user access to Rubin data previews. And I think this is guaranteed. Finally, I will say one word about the Think alert broker. This is something which is very similar to Lather, which has been presented by George in the previous talk. So Rubin is going to generate millions of alerts every night. These alerts will be generated within 60 seconds after data taking, and then this flux of alerts will be analyzed and enriched by a set of alert brokers. So in France, we are coordinating the development of Think, which is one of them. The team is here. The role of this alert broker will be to classify, to cross-match, and to enrich the alert stream. It will be oriented toward the multi-messenger astronomy, and it is currently being exercised and further developed using the ZTF stream. If you want to have more information about the Think alert broker, you can go to this webpage, and I think that there is also a way to access the broker through Jupyter Notebooks. So, just to conclude, we are now looking forward to the first Rubin LSST data to see how all this will be finally working. There is still a lot of work to be done, but this is really a very, very interesting experiments from the cosmology point of view, of course, from the science point of view, but also from the computing and data access point of view. Thank you very much.
Thank you, Dominique. Great talk again. I think we got a really, really nice overview of this project, which I had been following quite some time already, and I agree fully. It's very fascinating. Let's see what kind of questions we have. So there's one from Benjamin Weaver. What is CephFS and what motivates the change to GPFS? Oh, from GPFS, sorry.
The answer is very simple: money. GPFS is now extremely expensive, and we cannot afford it anymore.
And
but GPFS
is
very good. The GPFS is a very nice tool.
Mm-hmm. So what the first part of the question? What is CephFS?
Or CephFS, and I'm not expert at all on that, but this is also a parallel file system that has the same kind of functionality as a GPFS, but which is, I think, free.
Mm-hmm. All right. There's one from Luis as well. Do you feel comfortable with KDES now or not? Do you think you have it kind of mastered or not?
No, I am not comfortable. I'm not comfortable at all. I have to be frank. I started from zero. I started from scratch, and try to understand how this things is working, and this is extremely complicated. You can start deploying Kubernetes on a platform. It's extremely easy. You install kubeadm, you install your stuff. You are able to run some example. This is very simple. But as soon as you start deploying a large Kubernetes-based application, it can become extremely complicated. And the fact that cloud environment, cloud providers have developed some extra layers over Kubernetes is complicated the things for us who tries to run the things on a regular computing center. So to give you an example, there is a service on Kubernetes called a load balancer. If Google, for instance, detects that you need a load balancer at some point, it will create one for you from scratch, without any intervention from you. That's the same thing if you need some access to what they call a permanent volume. So your application will have a permanent volume claim and will stay pending until a permanent volume corresponding to the claim is available. If you are on Google, Google will detect that you need a permanent volume, check if you can afford for it and pay the money corresponding to that, and will provide the permanent volumes. If you are on your own, then you have to create that by yourself. This is just some very concrete, simple example. And sometimes your application is just not running, seems to be okay. All your Kubernetes pods are okay, are green, and something is missing. And you can spend days, literally days, to understand what happens.
Yeah, thanks. There is one more from Robert Nikita. Do you see any true alternatives to Kubernetes on the horizon?
Unfortunately not. So this is one of the reasons of my slide here. I think that if we want to survive in the medium term, it is vital to hire, to train true Kubernetes experts in our data centers. And this is not easy. I insist on the true Kubernetes experts. I mean, not someone who is just able to make a simple Kubernetes applications. We need to have true experts who really understand all the details of this system. This is the point of view of a physicist. Trying and I was a little bit surprised because in my previous scientific life I was used to be able as a scientist to take a system, install it, run it. It was not clean, it was not very nice, but at least I was able to make it run. I think this is the first time in my life where I take a system like that and I stay completely stuck for weeks.
But just a question, but it's one-off. I mean, just somebody that helps you to set it up, or you have to maintain this person in the staff?
I think you have to maintain this person on the staff, because things can turn very, very bad when you install a new service or when you have to upgrade versions. So you don't need to have 10 Kubernetes experts in your computing center, but I think that at least 2 experts for the whole duration of the project is something which is essential.
There's another question from me. Well,
yeah, there's a one from Mario George. He says, I very much agree with you and about Kubernetes and the maturity and complexity. It feels like Slackware in 1993, which I think that's a good comparison for sure. And I also like Dominique, your thing about survive with this technology. That is really a nice one.
But we will make it work. I am confident.
Yeah. We have the same thing in SK actually. This is a true nightmare actually. Even for computing experts, it's just a real nightmare.
No one's looking at the Slack because there's a question for Robert in Slack, and I put a comment in Slack.
Yeah, interesting. I can't see it.
I'll help you.
Oh, there we are. Okay. I see the one from Robert, and you have. Yeah, Will had a comment on there to say, well, the previous systems wouldn't scale, right? Well, I have my doubts that that thing would scale to what we needed to, but anyway, that's a different question. Dominique, what's your impression there about scalability
about scalability? Frankly, I think that scalability, the only way to test scalability is to run test. You cannot predict in advance with a great accuracy what the scalability will be. So we need to test. And the organization of Rubin is complex with this respect, in the sense that the software is developed by the Rubin project, and the end users, the scientists, will be in separate collaborations. And this is, it always worries me that at some point we discover that there is a mismatch between what is being developed and what is expected. So we have to be very careful with that. And scalability is an issue. It is not the only one, but this is an issue. And the only way is to train. So data preview 0, 1, 2, 3, 4, and repeat until we have the right scale for the for our system.
Yeah, thank you. So we're just past midnight here in Perth, Western Australia, which is not the same as for you. So I think that's actually when we are supposed to have our break. Luis, is that correct?
Yes, we should get back at 1:30 local our time in the afternoon. And I hope you stay awake for the afternoon session. We are counting on you.
Yeah, I will be there.
Okay, so 1:30 people, okay, for the last session. Thank you very much to all of the morning speakers, the great talks.
Thank you. Bye-bye.